In this video, we'll discuss exchange forces, which are very specifically a quantum phenomenon. We'll first start by talking about two-particle systems, and then we'll talk about bosons and fermions and how they differ. And then finally, we'll do exchange symmetry and then develop the forces that come out of the exchange symmetry. So let's just review the notion of exchange. We have solutions to the Schrödinger equation for two identical particles which are symmetric and antisymmetric under exchange. And so you can have simultaneous eigenfunctions of both h and p, the exchange operator. So h applied to psi plus, that's the positive or the symmetric term, gives me psi plus of R1, R2 times E plus. While when we apply the exchange operator to psi plus of R1, R2, we get psi plus of R2, R1. So we exchange R2 and R1 coordinates. Every coordinate's exchanged. And because it's symmetric, this is equal to plus psi plus of R1, R2. So the exchanged function is equal to the original function. If we apply the Hamiltonian to psi minus of R1, R2, we get E minus of psi minus times psi minus R1, R2. And when we apply the exchange operator to psi minus of R1, R2, we get psi minus of R2, R1, which is equal to negative psi minus of R1, R2. So particles whose wave functions are symmetric under exchange are called bosons, and those whose wave functions are antisymmetric are called fermions. The antisymmetric fermion wave function leads to the Pauli exclusion principle. That is, there are no two identical fermions can occupy the same quantum state. That's very important for the construction of atoms. However, any number of identical bosons can occupy the same quantum state. And that also leads to some very interesting physics, in particular to things like Bose-Einstein condensation and superconductivity. So let's see what are the consequences derived from this exchange symmetry. So the requirement of symmetric or antisymmetric wave functions seems like a bookkeeping issue, but there are real physical consequences of this requirement. Suppose you have two particles and two single particles orthonormal states psi A of x and psi B of x. So we're doing one-dimensional systems here. The two-particle wave functions for the three cases are as follows. For distinguishable particles, let's assume you have two particles that have the same mass but are distinguishable. For example, an electron and a positron might be an example. You have the distinguishable wave function psi sub d of x1, x2 is equal to psi a of x1 plus psi b of x2. For identical bosons, psi plus of x1, x2 has to be the symmetrized function because it has to also be symmetric under exchange. That is, you have 1 over the square root of 2 times psi ax1 psi bx2 plus psi bx1 psi ax2, so that when you exchange x1 and x2, you get the same function back again. This is not necessary for distinguishable particles. For identical fermions, you have to get an antisymmetric wave function, and so you have psi minus of x1, x2 is equal to 1 over the square root of 2 psi ax1 psi bx2 minus psi bx1 psi ax2. So when you exchange x1 and x2 here, you get the negative of the original function, just like we showed before. Now what we're going to do is we're going to calculate the expectation value of the square of the separation distance between the two particles for each of these possible cases. So what is that? Well, it's you have the separation distance is x1 minus x2, and then we'll square it to make it a positive definite quantity and take the expectation value of that. Well, if you think about that, that will be the expectation value of x1 squared plus the expectation value of x2 squared minus 2 times the expectation value of x1, x2. And so this is what we're going to calculate for distinguishable identical bosons and identical fermions. So let's start with the distinguishable particles. The wave function is simply a product state, right? It's psi ax1, psi bx2. And so the expectation value of the separation distance squared is this, which we'll put this x1 minus x2 quantity squared expectation value with a sub d. And that's what we wrote on the previous page. That's just the expansion of this for the distinguishable particles. Well, let's do those integrals. So x1 squared expectation value is equal to x1 squared times psi a x1 squared modulo squared dx1 integral of psi b of x2 quantities modulo squared dx2 integrated over dx2. Since psi a and psi b are independent because they're independent coordinate systems, then the x1 squared appears only in the one integral. Well, clearly this, if these are orthonormal functions, this is 1. And this just gives you the expectation value of x1 squared in state A. And we'll write that as x squared, expectation value of x squared A, sub A. Similarly, when we do the expectation value of x2 squared, now the x2 squared goes on in with the integral on psi b, and so we get the expectation value of x squared sub b in state B. And then we want to do the third integral, which is x1 times x2 expectation value, and the x1 goes with the dx1s, and the x2 goes with the dx2. So this is just the product of two expectation values, x expectation value of x in the A state and expectation value of x in the B state. So we can now build this, this quantity from up here, which gives me the x1 minus x2 squared expectation value in distinguishable particle states is equal to x expectation value of x squared in the A state plus expectation value of x squared in the B state minus 2 times the expectation value of x in the A state times x in the B state. Now, for identical particles, we have either symmetric or antisymmetric wave function, and we can do them both simultaneously. So, psi plus minus is equal to 1 over the square root of 2, psi ax1, psi bx2, plus or minus psi bx1, psi ax2. So if we evaluate the same expectation value that we did previously, which is x1, expectation value of x1 squared plus expectation value of x2 squared minus 2 times the expectation value of x1, x2, but now we're doing it in the plus minus states with these states involved. So expectation value of x1 squared is 1/2, because now this is, we have to square that wave function. And then we have expectation, then the integral of x1 squared. And now we have to multiply these out. So we have, with this squared, you get psi a of x1 modulo squared dx1. And then you have the integral of psi b of x2 modulo squared dx2. That's just this times itself. This times itself. Then we have a term where we have this one times itself. And again, you have a plus sign because the minus sign will be taken twice and cancels out. And now we have x1 squared, and you have modulo squared of psi b of x1 modulo squared dx1, and then the expectation value of the probability density of psi a of x2 modulo squared dx2. And then we have the cross terms. So one cross term will be this term times this term. And now we have x1 squared psi a star of x1 psi b of x1 dx1, right? And then we have psi b star of x2 psi a of x2 dx2. That's this term times this term. And then we have a fourth term which is also plus or minus. And now you have the x1. This is this term first times this term. And so you just have x1 squared psi b star of x1, psi a of x1 dx1. And then you have psi a star of x2, psi b of x2 dx2. Well, if you look at this, you realize that this is equal to 1 because it's just a normalization integral. This is equal to 1, so that's a normalization integral. And these two are not necessarily equal to 1. But if you look down at this term, you'll see that this, because these are orthonormal, this gives you 0. And this gives you 0, so the last two terms just go away. And so you have 1/2 times x squared, expectation value of x squared in state A, times 1, plus expectation value of x squared in state B times 1, plus or minus 0, plus or minus 0, which makes 1/2 times expectation value of x squared in the A state, plus expectation value of x squared in the B state. When we do x2 squared, we get exactly the same thing. So these two are going to add up to being, they're the same ones. They have a 1/2 in between them, so the sum of them gives you just this term in the brackets. What we have to do next is calculate x1, x2, the expectation value of x1, x2. Well, we can do that. And again, we have a few terms. We have the first term is x1 psi a of x1 squared dx1 plus x2 times x2 psi b of x2 modulus squared dx2. These are both integrals. Then we have the opposite, that is x1 psi b x1 modulus squared dx1 times integrals x2 psi a of x2 modulus squared dx2. Then we have cross terms, which are plus or minus x1 psi a star of x1 psi b of x1 dx1, x2 psi b star of x2 psi a of x2 dx2. And then the final cross term is x1 psi b star of x1 psi a of x1 dx1 times the integral of psi of x2 psi a star of x2 psi b of x2 dx2. Now clearly these are going to be the expectation values of x1 of x in state A. This is the expectation value of x in state B. Similarly, expectation value of x in state B, expectation value of x in state A. So these two terms will give us the same. These terms, however, are not necessarily 0. And we're going to call them something. So the first term gives me expectation value of x in state A times expectation value of x in state B. Second term gives me exactly the same thing. And the third term gives me the expectation value of x in state, in the cross state AB. So it's an overlap integral, right? It's an inner product of AB with x in the middle as an operator. Same thing with this, the second term here, but it's just BA. And then this term is again plus or minus x, expectation value of x sub BA times expectation value of x sub AB. And so when we put this together, we get these two add up together to give me 1 times x, expectation value of x in state A times expectation value of x in state B, plus or minus the magnitude, since these are complex conjugates of each other, the modulus squared of expectation value of x in the crossover between A and B, modulus squared, where xab is just this integral, xa star b dx. So we can now calculate that distance squared, expectation value of distance squared, for the plus and minus states. When we bring in what we had before, we have x modulus expectation value of x squared in state A plus expectation value of x squared in state B minus 2 times expectation value of x in state A times expectation value of x in state B. And then you have minus plus 2 times the modulus squared of the expectation value of x, or the inner product of x across A and B. So we have the three different cases. For distinguishable particles, it's this: you have x squared expectation value in state A plus x squared expectation value in state B minus 2 times expectation value of x in state A times expectation value of x in state B. For the identical particles, you have the same thing, which is all red, plus this additional term, minus plus 2 times the modulus squared of the inner product of x between A and B. Well, we can then substitute this term in for this, and so you get that the expectation value of the distance squared for states plus and minus, symmetric and antisymmetric under exchange, are equal to the expectation value of this distance squared in the distinguishable case minus plus 2 times this quantity here, this modulus squared, which is a number. So compared to distinguishable particles, the bosons, which are the top sign, that is minus 2 times this modulus squared, are closer together. And fermions, which are the bottom one, are further apart. So there's an actual force, a physical, I would call it an exchange force, but of course forces aren't part of quantum mechanics. But what happens is the probability of finding the bosons closer together is higher, and the probability of finding the fermions further apart is higher. So this exchange force, the so-called exchange force, is only non-zero if the two single particle wave functions have a significant overlap. That is, the two wave functions have to be close enough so that that overlap integral, x, the inner product of x across AB, is non-zero. If they're too far apart, you won't get anything, or it'll go away. So when you bring the fermions together, they tend to want to be further apart. When you bring the bosons together, they tend to want to collapse closer together. And this is the origin of this Pauli exclusion principle, or what you expect to see with fermions is they don't like to be in the same state, and there's an additional force that's associated with that. And fermions can condense into things like the Bose-Einstein condensate.